In this video, we are going to define the proposed case, that is the solar system, inverter, and battery. Just a few assumptions to begin. We're going to assume that they're going to use a pure sine wave 10 kilowatt inverter charger. So let's break that down a bit. Those of you who are familiar with the sizing of inverters for on-grid photovoltaic systems might be tempted to size the inverter based on the size of the photovoltaic array. In an off-grid system, obviously that doesn't make sense. The inverter has to be sized to meet the peak load. So the peak load is 10 kilowatts, so that's the sizing of our inverter. Pure sine wave refers to the quality of the sine wave output of the inverter. That's in contrast to, say, modified square wave inverters, which are cheaper but may not operate all electronic devices. So with the decreased costs of power electronics, pure sine wave inverters have become less expensive, and it's a reasonable option to pick here. The inverter charger part suggests that this is an inverter that can also function as a charger. That is, it's a bidirectional converter. Strictly speaking, given that we have no genset, no AC source of electricity in this system, the charger capability isn't required. However, inverter chargers are often associated with off-grid systems, and it would allow us to add a generator in the future, so it might be a reasonable choice. It's also a fairly expensive option, so once again, if we find that we can justify this proposed case photovoltaic system using an expensive inverter, then if we choose to use one that's less expensive, it would also make sense. I'm going to suggest we use lithium-ion batteries here. I'm going to propose that the batteries will be kept in an environment that doesn't get that cold, so perhaps within the home itself. So issues of cold weather performance won't be extreme. And I'm going to suggest that we can tolerate occasionally having a low battery state of charge. So by that I am implying that the homeowner or the people resident in the home will intelligently recognize that during periods of little sunshine, the battery may run down a bit, and they may have to adjust their activities a bit in order to prevent loss of load. That stands in contrast to, say, a telecommunications site, which has to have very high reliability, so the electrical load of the system has to be met fully at all times, at least with a very high probability. Under the Energy tab, we're on to step 3, defining the proposed case. And when we look at the navigation pane here, we see that currently we don't have an inverter and battery specified. So I'm going to add those by clicking here, and a new line is added here. Currently, just the inverter is added. If I click here as well, the battery section of the form opens as well. The inverter we indicated was going to be 10 kilowatts, so I'm going to put that in here. For the efficiency of the inverter, we could try help. This guidance here, however, I think is a little bit more suitable for on-grid inverters, and I'm going to base this on a little bit lower efficiency that you tend to see for inverter chargers. For miscellaneous losses, I can once again use help and see that this might be associated with, say, a DC-DC converter or step-up transformer. In most cases, this value would be 0. I'm going to go with that, and we could modify that later if we found that to be incorrect. Now I have to specify the initial costs of this inverter charger. Ideally, I would go and look up these costs through a supplier, get a quotation if necessary, or at least check supplier costs for the type of equipment we're proposing. But if we want to be really fast about this, and that is one of the goals of a pre-feasibility analysis, we can click on this $sign icon here to open a cost database. And we can see that based on different sizes, typical costs for in US dollars per kilowatt for different types of inverters are provided. So for a pure sine wave inverter charger, of roughly 10 kilowatts here, we see that it looks like it would be around $300 to $370. So I'm going to, now remember that's per kilowatt. I'm going to close this and say we got 10 kilowatts, and I'm going to say maybe $350 US dollars, so $3,500 US dollars is my estimate of the initial cost of the inverter. It's much more than an inverter for an on-grid system, but this is much more functionality. Now for the battery, the first item we have to specify is days of autonomy. So days of autonomy, as we could find by looking at the help, is the number of days that the fully charged battery could fully supply the load without having any input of power, say, from the photovoltaic system. If we were working on a system that had a very high requirement for reliability, say a telecommunication system that we really couldn't accept being down very frequently, we might want to specify a large number for the days of autonomy, maybe even going to 10 days of autonomy, which would be pretty extreme. But this is a home system, so we can tolerate, as we mentioned, the occasional period when the occupants have to adjust their behavior because the battery is running down to near a zero state of charge. So on that basis, I'm going to say, let's start out with 2 days of autonomy here, which is a reasonable estimate for this type of system. We then specify the voltage. This is really not a critical parameter for RETScreen. For design of a system, it's a critical parameter, but RETScreen is not engineering design software. And in fact, all it's using here is to convert an estimate of the required size of the battery in kilowatt hours into a suggested capacity in terms of amp hours. So that's not particularly critical. I'm going to put in 48 volts here. For the efficiency, I could look in help here and see that in the absence of information from the battery supplier, an efficiency of 85% may be used. I think for lithium-ion batteries, that's a bit on the low side. I'm going to use 90%. For maximum depth of discharge, lithium-ion batteries can be discharged very deeply, unlike, say, lead-acid batteries. So I'm going to put in 100% here. Hopefully most of the time, because we've got 2 days of autonomy, we're not discharging that deeply, because that might lead the battery to wear out a little bit more quickly. Most of the time I would guess that we're discharging it to much less than 80% depth of discharge. But if need be in those critical situations, we'll let it go down to 100%. For the charge controller efficiency, once again, I can use help, look at that, and it says 95% is suggested. Once again, I think that's a little bit pessimistic. I'm going to put in 98% here. And then we'll have a line item for temperature control method. So this refers to how the temperature of the battery is to be estimated by RETScreen. And what it uses this for is to estimate how much the capacity of the battery, the available capacity of the battery, is going to be affected by fluctuations in temperature. As I mentioned in the previous slides, I'm expecting this battery to be kept inside the home, or at least in a part of the home that isn't subjected to the full range of outdoor ambient air temperature swings. So I'm going to suggest that in fact the battery temperature is constant, and I'm going to suggest that it's around 20 degrees. And this could also be achieved by a battery thermal management system, which consumed a bit of the battery energy, or energy going into the battery, in order to maintain the battery temperature. That is also a possibility, particularly for lithium-ion batteries. We see then that the average battery temperature derating is 2%. In other words, we're not oversizing the battery because we expect it to be cold. The suggested battery capacity by RETScreen is 274 amp hours based on the information we've provided. I'm going to use that estimate here, and that corresponds to a 13.2 kilowatt hour battery based on the voltage of 48 volts. Now I just have to specify the cost of this battery. So once again, I can use this cost database. I click on that, it opens up, and I see there's a range of different batteries available here. Lithium-ion batteries of small sizes are in the first 2 rows, and I see the typical installed costs tend to be in the 670 to 890 range here. Pick a value in there, say around $700 per kilowatt hour. You can see that there's some other information available in this table. So I'm going to put in the $700 per kilowatt hour here, and that works out to $9,206 for the battery installed. All right, in the next video we're going to specify the photovoltaic system array.